Thank you very much for the introduction. I'm happy to be with you yet again virtually. Hopefully one day we will even meet in person. And with my colleague here, Ludovic, I'm Bruno HUTTNER from ID Quantique, and I am also the co-chairman of the Quantum Safe Security Working Group of the Cloud Security Alliance. So we have been discussing for quite a few years now with my dear friend Ludovic, who is the co-chairman, about what's happening to our good old internet in the quantum era and what we need to do in order to make it secure. So maybe Ludovic, just a few words about you, and we'll start. So Ludovic, unfortunately, is still on mute. It's not usual for him.
That was the opportunity to test the mic. So I'm the co-founder of CryptoNext Security. As Bruno said, we are working together in the Cloud Security Alliance on this topic of quantum security in a quantum world. And so I co-founded also CryptoNext Security, but I will give a few words after. So now I will let Bruno start.
Okay, so let's start with the presentation, which you're all waiting for. The idea really is to make a kind of introduction to what's happening to our internet in the quantum era. On the agenda of the presentation, please next slide, is first of all to show you why would quantum computer be a new paradigm? What's different between quantum computer and a standard computer? We will see that the quantum computer or the quantum period is actually both opportunities and threats. And we will then discuss the timeline, the impact of the quantum computer when we have to start to deal with that. As you probably all know, there is no big quantum computer available now, but there are already some small ones. But even so, you cannot do very large computation yet. We believe it's very important that you start thinking about how to deal with the future quantum era right now. And of course, we want to give you some solutions. So we will deal with quantum safe solution. We will discuss three types of three solutions, basically. One which is more classical, which is post-quantum, and the others are based on quantum technology, which will be quantum randomness and quantum key distribution. And we'll end up with hopefully some action points for you, food for the thought. So if we can move to the next slide. What I want here is really discuss a little bit about the new paradigm for information processing. A quantum computer is not only a more powerful computer, it's really changing everything we know about the way we do computation. And I'm not going to explain to you in detail how it would work. We would be there until tomorrow probably, but just give you maybe an analogy. So if we can move to the next slide. Please, next slide. So we start with the analogy, and this analogy is coming back to ancient Greece. If you look at Greek temples, you find out that, of course, they are magnificent, but you find out that there is something a bit peculiar in all the Greek temples, is that the distance between the two pillars is always a given distance. It's never bigger than something. And the reason is that when you put a big stone and you put it on top of the big pillars, if it's too far away, basically the stone will break. Of course, you can try to make it stronger, but if you make the stone too big, then of course you cannot put it up, it's too heavy and so on. So there is basically a maximum distance you can have between the pillars, and this is the distance you can see in all the famous Greek temples. So what people did is you waited a bit for the Romans, please next slide. And the Romans simply changed the basic building block of the temple, and the change was very easy. Anybody could have thought about it, but nobody did before them. And it's to change the shape of the stone between being a square to being a trapezoidal shape. And this was the idea of the so-called Roman arc we all know. And just with this change of the basic building block, you changed completely the way you could build not network, but buildings, basically. You could change all the building way from something which was limited in scale to something much bigger. And here I show you a little bit the evolution of this Roman arc from the first time where it was really not so nice to something as magnificent a few centuries later as the Saint Chapel in Paris. Of course, this is an analogy. I'm not saying that this is linked to the quantum computer at all. But what I show you is that by changing a basic building block, you can actually change the whole way you do something. And that's what's happening today with quantum computation. So next slide. Quantum computation is really changing the building block of computer. In all computers we have today, we are dealing with bits. A bit is a basic unit of computation, and a bit can be a 0 or a 1. Here I show you on this graph on the left-hand side, we can make a physical model of the bit here as this double well of the potential, and you put a marble in one of the two holes. If it's on the left-hand side, it's a 0. If it's on the right-hand side, it's a 1. And basically what's really interesting is that any computer can be modeled by that. What you need, the only thing you need is to be able to move this marble from one to the other. And that's really the computation. If you take a large enough numbers of these potential wells, these little boxes, and you have enough marbles, and you make them interact the way you want, I mean, just switching from one to the other, you can actually build any kind of computer. All computers are exactly with the same, can be built with exactly the same kind of design and will have the same property. Of course, they don't all work at the same speed, but the basic element is exactly the same. This is changing completely once you go to the quantum model. In the quantum model, you don't have these bits which can be 0 or 1 only, but they can now be a coherent superposition of zeros and 1. It means out of this standard way, you can build new states which really are totally different than the original one. And here I show you, for example, two possibilities with a combination of 0 and 1 with what is called different phases. So the two look similar, but in fact, they're also very different states, which you have here. And once you have this coherent superposition, you can start doing things which you cannot do with a classical computer at all. Or basically, even more generally, you can do things which you cannot do with standard information processing. And I will briefly explain what you can do on the two very brief examples. Next slide, please. So the first thing you can do with this new kind of bits, with these qubits, is you can make a coherent superposition. Okay, you see here that I put my bit in a coherent superposition of 0 and 1. And if now I want to measure these bits, then quantum mechanics is telling you that you have random possibilities to have either a 0 or a 1. So measuring this qubit will give you with the same probability 0 and with the same probability 1, and it's totally random. So you see that just this coherent superposition gives you something which is actually rather difficult to get classically, which is to generate random numbers. Quantum mechanics is intrinsically undeterministic, and there is no way you can know in advance which way the qubit will be measured. So one first thing is getting randomness out of these qubits. Second thing you can get out of this qubit is to get secure communication, and this is known as quantum key distribution. If now you take a qubit which can be, for example, in one of these three states, and you use this qubit to try and transfer keys from one point to the other, there is a theorem in quantum mechanics which is called the non-cloning theorem, which means that you cannot copy this qubit to any arbitrarily quality, which means basically that if somebody is trying to find out what there is, which qubit was sent, he cannot do it without creating some errors. And this creation of errors will be used by the lawful users of these qubits, which are normally known as Alice and Bob, to send secure keys. If Eve is trying to eavesdrop on that, she will make errors, and Alice and Bob will find out. So you see already that just with a single qubit, you can do things which are very difficult classically. First, you can generate randomness. Second, you can perform quantum key distribution, which will allow you secure communication. The third thing you can do with this qubit, I mean, there are probably many other things you can do, but the third thing we will discuss briefly is the quantum computer. Here, I cannot say too much. It would really be too long. But the idea is that by using this coherent superposition of many qubits, you can actually generate states which will allow you to do a computation in much fewer steps than you would do classically. This is really where the power of the quantum computer comes. So you see now that just by changing the basic building block of my computers from bits to qubit, I actually change completely what this thing can do, what a quantum computer will do with respect to a classical computer. Next slide, please. So the fact that you can perform computations much faster or with less steps than with a classical computer is both an opportunity and a threat. Let's start with opportunities. So here I show you, well, it's a little bit the same. Here I show you that basically the two aspects of the quantum computer, these nice opportunities and also the evil side of the quantum computer. So next slide. On the bright side, the quantum computer can be used to perform computation which are impossible to do with a classical computer. For example, you can find new materials. By being able to calculate the structure of a material which would be difficult to do or impossible to do with a classical computer, you can invent materials which have very distinct properties and which you can use for many kinds of applications. You can also do optimization in a better way. If you have a very complex problem and you want to optimize the solution, again, the quantum computer will be able to look at all the solutions together and find the best one much, much faster than a classical computer. A third application is about machine learning and artificial intelligence, which is very, a big hype nowadays. A quantum computer can help you to learn much faster than a classical computer. It means that you will use it really, for example, to apply driverless car, which will learn much faster what to do once they're on the road and how to behave if they see something special, basically. These are all the good things that a quantum computer can do. There are many others which we don't have time to discuss now. However, there is also the evil side. Next slide, please. And on this one, I will let my colleague Ludovic to start the discussion on the dark side of the quantum computer.
So thank you, Bruno. So indeed, there is kind of dark side of quantum computer because this ability to solve much faster certain problem can be used for breaking cryptography. And so in particular, it happens that you have very fast quantum algorithm for solving the basic problem which are underlying public key cryptography. So here we show the factoring problem. So which is underlying the famous Revest and Shamir Adelman algorithm. So next slide. So to be clear, so when we say that the quantum algorithm will be able to break public key cryptography, is that it will be able to badly break what are deployed today as the standards. So usually when you speak about security, so you want that confidentiality or authenticity is guaranteed for many centuries. So once you will have a quantum computer which is powerful enough, then you will be able to break public key cryptographic standards in a few minutes. And so this is kind of catastrophic. And so at the scale of internet, it simply will make impossible to communicate securely. So there is many applications of public key cryptography. It's almost everywhere. And so one of the applications that we are going to emphasize a bit is messaging application. But of course, in the context of internet days, so we all know about the small lock that is securing our communication with HTTPS. So please, next slides. And so next slide. So just to come back a bit with the introduction, it's not a urban legend. So it's not something completely crazy that will never happen. So quantum computer, they already exist. So it's not science fiction. So every day they are becoming more and more powerful. And so what we can use to measure this increase in capacity is typically the number of qubits which can be used to do computation. And so already this week, IBM announced a new breakthrough. And so they say that they will have a quantum computer with 127 qubits, so which is much more, well, which is much than the previous records. And actually, you have, I will not say every week announced like that, but on a constant basis. So we saw progress in the direction of computing a quantum computer, because this is a strategic topic. So today, so there is a technological race between Asia, Europe, and US. And so this push everybody to in the direction to have more and more powerful quantum algorithm. But still, the quantum computers which are available today are not powerful enough to break crypto, and not yet to deliver a practical application. But many people believe that the first practical application are not going to be crypto, but probably in the topics that Bruno mentioned before, in a few years. So we are very close. So please, next slide. But as I said, so quantum computer exists, but they are not powerful enough to break cryptography as I described. So one question that you can wonder is, why do I care? So it is indeed a urban legend. So not, because in fact, you have an impact already right now, because we can harvest data now. So this can be done quite easily at the internal level, at the level of a country. So you can harvest all data. And so once you have this data, so you can just wait, store this data, and wait that there is a powerful enough quantum computer available to decrypt the communication. So this is really a time bomb on security. So next slide. Yeah, and so one question is when my administration, my company should think about finding a solution to this issue. And so just to keep in mind some deadlines. So already next year, Google announced what they claim as a quantum advantage. So showing that quantum computer can really perform a computation faster than classical computer. So the announced by IBM is a quantum computer which is twice more powerful than the computer that Google used last year. And so regarding this very fast progress on the power of quantum computer, experts believe that we have between 4 and 9 years to find a solution and to deploy what we call a quantum safe solution before actually it's too late. So one deadline that you can keep in mind is that you should deploy now a quantum safe cryptography for any data which is supposed to be secure before and after 2030. So next slide. So now we arrive to the question of what are the solutions? And next slide. So there is two solutions. One was mentioned by Bruno before, and it's related to quantum phenomena. It's quantum cryptography. And so the other solution is post-quantum cryptography. So I will continue with the analogy of Bruno between Greek temple and Roman temple. So in post-quantum cryptography, you are going to use not exactly the same building block, but a close building block. So what you are going to use is a different R problem. So instead of factorization, you are going to use another problem. For example, solving a system of nonlinear equation. And after, you will be able to build exactly the same public crypto system as before, but with a guarantee on the security, at least if we believe on the hardness of certain problems in post-quantum crypto. And so this is post-quantum cryptography. And the other solution, which is very complementary, is quantum crypto. But maybe at this stage, I will let Bruno continue.
Yes, indeed. Thank you, Ludovic. So basically, we have seen that there are, well, hopefully there are solutions. Ludovic expressed the classical solution, which is post-quantum algorithms. But strangely enough, the same properties of the quantum world, which will destroy our security, will also allow you to retain security. So you use quantum both for destroying and then to rebuild, which is kind of interesting. Today, there are two things which can be done with quantum technologies, which can be used already today. One is generating the best available keys, which is called the quantum random number generator. Second is quantum cryptography or quantum key distribution. A bit further ahead, if we look in the future, there will be a much bigger network, we call them quantum network, and probably ultimately in a few more years, quantum internet, which we will not discuss too much today. So let's go first to the current solutions with quantum technologies and move to the next slide. Next slide, please. Yeah. There have been some, let's say, tension between, no, go back, please. Oops. Post-quantum, where are we now? Wait. I think we lost the, so we need
here.
to go to quantum. Okay, now it's good. Yes, please. Okay, so basically there have been some tension between classical and quantum solutions. And we now believe, and that's why you see Ludovic and I are working together on this matter, is that we believe that actually you should use the both possibilities to make the best cybersecurity. Some crypto functions are probably best solved by quantum. Some others probably best solved by mathematics, new algorithms. And altogether, by using with both of them together, we will have the better system. Here I give a few examples. For example, in order to generate randomness for key generation, quantum is probably better than mathematics because it is on even other kinds of physics, because quantum mechanics is intrinsically random. If you are dealing with authentication and signature, then you have very good mathematical solutions, both pre-quantum and post-quantum, if you want. There may be also some interesting physical solution, which is called physically unclonable functions. So you see, there is always a mixture of both. For key exchange mechanism, how you can exchange keys from one point to the other, here again, you have both mathematical and quantum solutions. And probably both will be used in our cybersecurity infrastructure of the future. Finally, just a few words about encryption. Today, if we want to encrypt fast enough, the only known solution is really to use mathematics. So that's where, in any case, we need some kind of good algorithms, and we have them actually already to encrypt the data. Next slide, please. Let's now move to first classical solutions. And I think Ludovic will now explain a bit more about post-quantum cryptography. Ludovic, back to you. No, but you're on mute again.
No, it's okay. So as I start to explain earlier, so the goal of, well, so the principle of post-quantum cryptography is to define new art problems to construct public key crypto systems, so key exchange scheme and signature. And so there is an ongoing competition standardization process led by the US National Institute of Standards, whose goal is to define typically which problem is going to be used in the next standard and for which we are the most confident to be secure on the long term. So here, for example, I give you an example of one family, which is a multivariate based. And so instead of having a large integer like in RSA as a public key, you will have a set of nonlinear equation. So it's basically the same principles, just the objects are going to be different. The next slide, please. So one key message that we have to deliver here is that this standardization process is reaching its end. So by the beginning of next year, we are going to have new public key standards to use, which are quantum safe. So starting beginning of next year, you will now have new standards, and I think each company should have to decide whether or not they want to follow these new standards. But standards are here. And I emphasize the US process because, well, historically, NIST has the lead on the definition of cryptographic algorithm, but this is a worldwide effort. So the contribution to NIST are from everybody in the world, so including academics. So I did that when I was associate professor at Sorbonne University. And there is similar process in other parts of the world. So typically, China and also Russia are running currently kind of similar process to define regional post-quantum standards. Next slide. So now we are in a step that you will have to update all your current cryptographic product with this new standards. And I have to say that this is a huge task. And so what we propose in CryptoNext is to help you in this transition to make this as seamless as possible. And so what we propose is a software library which include all the standards which has been proposed to NIST. So we have efficient implementation of this algorithm in different platforms. And so when we do the integration of these new standards, we are not replacing the current cryptography, which is already there. We follow the international recommendation by National Security Agency, which says that you have to add a new layer to the cryptographic security part. So you add post-quantum cryptography as an additional layer of what you have already. So this is called the hybrid approach. And with that, so we help in the integration, and we also provide professional service to help on the integration. So next slide. And this is one example of projects that we did for a bank. And so we did the integration of the CryptoNext of this new post-quantum standards in the full list of application in a real application. So the goal was to put a timestamp on a PDF. And so when you want to do that, and you want a certain level of security, so you have to use different type of tools. So we integrate our library into an hardware security module, so which is mandatory in certain contexts. And so after we adapt our tool to an applicative layer which does the signature. So it's a third-party applicative layer, well, by a major player in the sector. And so the customer, which was here a bank, well, for him, he wants just to use the full service. And in fact, he used what we have already before, almost in the same way, but behind the scene, it's all CryptoNext, which adapted the infrastructure to make the timestamping quantum safe. So next slide.
So we are now moving to the quantum solutions, and we will start with randomness. And just for the few of you who may not know, randomness is absolutely crucial for any cryptographic process. Whatever you want to do with cryptography, you need to start with randomness. Classically, it's not so easy to get randomness because classical world is deterministic. If you know well what is the initial condition, you can also predict what will happen. And the solution to that is to go to quantum. So I'm going to move already to quantum. Next slide, please. When you base your randomness generation on quantum, you know you have very good randomness from the beginning, because at the heart of your process, you have something which is random. And at ID Quantique, we managed to do this quantum source, quantum randomness source, in a very, very small form factor, which can now be used everywhere. I'm not going to explain to you how this is done. Please get in touch with us if you want. But I will really show you the first practical implementation, or one of the first practical implementation of this quantum randomness, which is really to integrate the quantum random number generator in a phone. So next slide, please. This is a phone, well, it's made by Samsung, and it's called the quantum phone. It's like a standard phone, but in addition to all the standard properties you find in a phone, it has a quantum random number generator, which you use in order to generate any kind of crypto process. And we use this phone in collaboration with CryptoNext to make a better messaging system. And I wanted really to emphasize that because, again, this shows how to mix quantum effect. Here we use the quantum random number generator with post-quantum cryptography. And what CryptoNext has done is to add to the standard classical layer for the messaging security a new post-quantum layer, which would add to the security and make sure that the messages exchanged with this phone will be secure not only against a classical computer, but also against a quantum computer. And if you add to that the quantum random number generator for all the keys you are going to use, you really have some very good system which will be safe even in the future. Next slide, please. So let's move now very briefly to quantum key distribution. Next slide. Quantum key distribution is, again, using quantum properties in order to exchange, to have secure communication. So the way we do it is we work in the framework of symmetric crypto. So Alice wants to send a secret message to Bob. She has to encrypt it with a secret key. Bob can decrypt it easily if he has the same secret key. And the QKD is allowing you to transfer this secret key from Alice to Bob in a perfectly secure way using the quantum properties I discussed before, which is really that, oh, something's happening, but which is really that any attempt at eavesdropping on the transaction will be discovered by, will introduce errors and will be discovered by Alice and Bob. And that's really the principle of quantum key distribution. So if we can move to the next slide. What is the advantage of quantum key distribution? The idea is that if you don't eavesdrop on the channel, or if your eavesdropping is not successful, then your key is totally secure. All other cryptographic systems are based on computational security, which means that somehow the security will go down as time goes on because you will have improved algorithm, because you will have better computers and so on. So if you have some data which you wish to keep secret for a really long time, quantum cryptography and quantum key distribution, whenever possible, is a really good solution to use. And that's what we are advocating at ID Quantique, to mix always this standard, this classical solution with quantum solution in order to get the best possible security for your system, especially for your long-term confidentiality. So we could move to the next slide, please. The way we do it here is basically we have the standard communication channel with link encryptors which would encrypt your data, and you add one layer of quantum security by adding this secret key which you see entering into your classical system. So this is really the first practical implementation of quantum key distribution for securing the data between these two large centers. And if you move to the next slide, I can show you here that this is not, again, science fiction. We now have, this is our fourth generation of quantum key distribution system. And these systems are really like any kind of standard telecom system. They can be put in a rack and you connect them to the network, and you can use it to transfer, to make secret keys from Alice to Bob already today. So although quantum computers are not fully mature yet, you can do some computation, but not everything. Quantum key distribution is a mature technology in a sense that you can use it today to secure some of your network. And moving to the next slide. In the future, and the future actually is already here in China, which is what I show on this slide, people have already built this very large quantum network. And you see here a network covering from Beijing to Shanghai with both ground systems and also satellites for the longest distances. And in China, at least, people are now using quantum key distribution to secure information flowing from large parts of China from the north to the south. So you see that quantum key distribution is really something which is already available. But if you look a little bit further in the future, and that's the next slide, what we aim to do is not only that, but really to build a full quantum infrastructure, a global quantum infrastructure, which can be used to exchange qubits and provide improved security globally worldwide. And we are not there yet. This is not something which you can do today because it requires one basic building block which we haven't managed to do right now, which is a quantum memory. But as soon as you have a quantum memory where you can store these qubits and release them a little bit later, this would be really an enabler to build a fully secure global network based on quantum. And this network can be used to do quantum key distribution and probably many other things in the future. Next slide. So this is a conclusion on a few of the action points we would like to discuss with you very briefly. So the first thing you can do if you want to improve your security, First of all, the first thing you need to do is do not delay, which means that even though you don't have a quantum computer which is usable today to break cryptography, this will happen. And therefore, you need to look at what's available and start to think about what is the way to protect your system. A second thing which looks very simple, but unfortunately in many cases is not so simple, is to know your crypto, to know what is used in your company. And in many cases, especially in large companies where you had mergers and so on, you don't really know what is used in different parts of the company. And if you don't know what is used, then you don't know what is at risk. And if you don't know what is at risk, you cannot protect it. So the first thing is really don't wait. Try to know what you have so that you can find out which part of your network is best protected today. Then look at what are the possible solutions. As you know, it's first important to know what you have, and then you can look at solutions. The solution we advocate is really to improve key generation, for example, with quantum random number generation. Then to go for crypto agility. Don't be stuck with one kind of crypto you cannot modify later. There is so much uncertainty in this field that you need to be flexible enough to change if you realize that something is not the best solution. Or something which is the best solution today may not be the best solution even in 1 or 2 years. And therefore, you need to be really flexible whenever you try and implement a new solution. And unfortunately, number 5, you cannot find today a solution which will work everywhere. So you have to be a bit more clever and adapt your solution to the problem you are looking at. So really the message is one size does not fit all. It means you really need to adapt the kind of crypto you will need to the particular problem you're going to have. But if you do that, we believe that you can actually go to have a safer quantum internet in the future, improving the whole infrastructure and making sure that we can continue to have the exchanges we have today safely. Thank you. And this is the end, basically, of the talk. So next slide, which is the last slide. So thank you for your attention. And I wish you also a very good continuation of the Luxembourg Internet Days.
Thank you, gentlemen. It was very interesting. You made me make quantum leaps in my knowledge about quantum key distribution and other technologies all around. As we have a little time, because you were too fast, compared to our chronology of events. Let me toss two questions out to you.
We can continue for 3 hours. We were told we had 40 minutes, and I tried to keep the timing, and that's why I skipped a few things, but we can continue, or maybe there are some questions.
Exactly.
Or whatever.
Exactly. I was going to put two questions in front of you. Question number one is, IBM just announced a few days ago its new quantum CPU of 127 qubits. What's your opinion on the subject? Is that a real breakthrough? That's question number one. And the other one is, does quantum computing work as normal computing, hardware with a quantum CPU, quantum operating system on which you run your quantum algorithm, etc.? So that's the two questions.
I think Ludovic already mentioned the first part, so you want to take it, Ludovic?
Yeah, so breakthrough. So I will say, well, so we have to see the details, but with this number of qubits, it's much more than what was known before. So a lot of people announce 120 something, but here it seems that it's something that is going to be really available. So I think maybe breakthrough is maybe too strong words. Because it's a continuation, but regarding the complexity of doing such a things, we can consider that this is a major steps. And so what is also interesting is that IBM published a roadmap about 1 year ago to reach 1 million of qubits, and it seems they are on time with this intermediate step here.
Okay, thank you.
Now, and Bruno, you want to take the second part?
Yeah, with the second question, actually, this is still a very new field, so nobody knows what will be a quantum processor. It can be a very different kind of physical processes behind it. What we believe is that there will not be a pure quantum computer doing only quantum, but it will be mainly probably one quantum CPU, if you want, working in tandem with classical things. The quantum computer will not work with a very, very large input, for example. So you may have to cut the input into small pieces, use the quantum computer for these small pieces where it is best, and use with a classical computer to link all these together, for example. Okay, but again, it's very early, and there are many different architectures, and I think we're going to see a lot of new things coming out in the next few years. And to be honest, I wouldn't be surprised if the real quantum computer we will see in 5 to 10 years have nothing to do with anything we see now. You know, there are just very different ways to do it, and we'll see who will be the winner. It's going to be very interesting times.
Let me thank you, gentlemen, and this fills our times. Thank you very much for your availability. Thank you for having had this very vivid and very lively presentation. Let me end with a remark on your Sainte-Chapelle example earlier. Let's see whether the first quantum computer gives us 25 reasons why Sainte-Chapelle, from a statics point of view, could not exist while it still is there. So maybe lucky us, the guys at the time did not have quantum computers or computers at all to design Gothic flamboyant as a style. Thank you very much, gentlemen. It was a pleasure having you with us, a repeated pleasure as in the past years. Wish you all the success in your ventures on quantum, and hope to see you soon back at the Luxembourg Internet Days. Thank you.
Thank you. Bye-bye, everybody.
Bye-bye.